I'd like to talk to you for a few minutes about what it is to be an electrical or computer engineer. I have worked in industry for 30 years and in a wide variety of roles, and I'm going to share some of my thoughts with you. We are the creators. Engineering is a creative process where we use our specialized skills to provide solutions to society's problems. Electrical and computer engineers use their knowledge of how electricity works in a variety of fields in order to provide solutions. What's it like? Well, you'll likely use more of the variety of classes you take in college than almost in any other career. You will have times when it's just you and your computer, but typically you're going to work in teams of 5 to 15 other people, many of which will be engineers, but technicians and operators, marketing people, technical writers, all acting together as a team, along with interacting with other teams. In conclusion, electrical engineering can be a very social field. What are some of the roles in electrical engineering and computer engineering? Well, we always think of design. We want to design a product, but there are many other things that are needed to be done in companies to bring these type of products to market. Sales is a big one, where you will interact with customers at a very technical level in order to make sure that they're getting the solutions that they need. Of course, we need to test things. Testing complex systems is a very challenging type of field. To do it accurately and also to do it very quickly so that the product can be priced effectively. Process engineering is very important in electrical engineering. Many of the things that we build in electronics are done at wafer scale using photolithography, and the processes involved in that are some of the most challenging things done today, operating at dimensions much smaller than a wavelength of light. We also need quality assurance engineers that can make sure that everyone else is doing their job properly and that the products we're shipping are meeting our requirements and specifications. Production engineers work to make sure that the devices can be built consistently, reliably, and at a very minimal cost without sacrificing the performance. Field and application engineers are another customer-facing role where you will work a little bit more technical level than a sales engineer does, but help customers learn how to use your technology. A lot of times we think of product development as going to consumers, but there's a whole supply chain of systems in electrical engineering, and many times you are working in a company that's building components or technology that then is delivered to other engineering companies, and you have to actually teach those engineers at your customer's company how to use the devices that your company is making. And of course, we always need to have research going on to advance the state of the art, to meet challenges in ways that haven't been accomplished yet. And some may choose to work a few years directly in electrical engineering and then take the management ladder up the ladder of success and lead teams and eventually lead whole divisions. Finally, we have educators. My role at this point in time to teach the next generation of electrical engineers. So there are those that work at the physics level, working with the components. This might be at a transistor level, or it might be in specialty type components, let's say an LED, something like that, where we're operating right at the physics level. But then there's also those that work at the product level, those that are building the iPads and the Android phones, that type of thing, and everything in between. Finally, there are those that create the tools and those that use the tools. And what I mean by this is that there's software tools that engineers use on a daily basis, and we use those tools, but someone has to write those tools. And so those are software engineers, typically with a strong technical background also, so that they understand what they're actually modeling and simulating in their. So there's a number of current hot topics in electrical and computer engineering that I'd like to survey very briefly. Robotics is a big one. Robotics involves sensors and actuators in space and autos and hazardous environments. This is a picture of Robonaut, which is a bio-inspired human-like form, which actually has hands, human hands. Its first generation didn't actually have legs, but now they've put legs on him, and he's designed to, or perhaps we could call her a she, is designed to work alongside astronauts on very long duration space. I think we've all heard about the self-driving cars. Google is a prime driver in this field, although a number of other car companies are working on this. These cars are loaded with sensors and also considerable software and hardware processing to take all this information coming from the sensors to make sense of it and ultimately make decisions in order to get the occupants of the car safely from point A to point B and in a expedient fashion, and making sure we don't run over anyone in the meantime. Artificial intelligence is a field that crosses a lot of different domains, but computer engineers find a lot of employment in this field also. Machine learning is one aspect of artificial intelligence. You see on the left the Nest thermostat, that learns your patterns and knows when you head to work, and it can adjust the temperature of an empty house, but knows when you're coming home from work and can start conditioning the air ready for your arrival. On the right, we see Watson, who was the Jeopardy champion, the IBM artificial intelligence computer. This computer is more than just a curiosity on Jeopardy, but it's being used in the medical industry to help doctors do diagnoses, and many other applications are envisioned. Biomedical is an important domain for electrical and computer engineers. There's actually a biomedical discipline that many colleges offer, but here we're looking at an advanced prosthetic where it's an incredible advance from previous years, where now the user can have regained full dexterity in their hands and fingers. Bioinformatics is a fascinating new field where we're analyzing large data sets of biological data. You can think of the ultimate is when you go to the doctor and they take a sample, perhaps some blood or perhaps just some skin cells, and sequence your personal DNA, and then create a not only a diagnosis, but a customized treatment just for you and just for the condition that you're experiencing right now. This takes a lot of engineering, very cross-disciplinary, involves a lot of different fields of engineering and science, but ultimately you're dealing with very large data sets, and computer engineers are experts at handling it. Along the same lines, a lot of big data using statistics to uncover patterns. We need techniques to manage massive amounts of data. The amount of data that companies are handling right now is many orders of magnitude greater than it was just a few years ago. We've had an interesting development in supercomputing over the last decade. It used to be that supercomputers were very customized systems that took years to develop, and then even more years to try to program, and they were phenomenally expensive, and only a few of them in the world. it turns out we can use that graphics card that you bought to do your gaming on, your video gaming. We can actually repurpose that to do supercomputing. All of the hundreds of cores that are normally calculating the images to display on your computer display can be retasked to actually do parallel computing computations. And now our supercomputers are typically built with many of these type of boards, and basically resulting in a commoditization of the supercomputer. High-frequency trading is a fairly controversial subject, but all traders want to be able to get their data as fast as possible, be able to make their decisions and execute their orders as quickly as possible. And there is a tremendous amount of technology involved in making sure this happens. Some of the fastest networks and fastest computers are used in Wall Street, and computer engineers can make a good living there on Wall Street developing the technology. Quantum computing is a new style of computing where we look at using more than just 0 and 1s to represent our data. And if you click on this picture, you can get an interesting YouTube video that describes a little bit about this. But these computers are built from superconducting chips that operate down near absolute zero, cryogenically cooled, so that all amounts of resistance, electrical resistance, vanishes. Cloud-based computing is another application of big data, but has grown in popularity tremendously now, where your applications no longer run on your local device, but rather on some server out there, or actually, more accurately, a whole bunch of servers out there in what we call the cloud, some nebulous thing in the network that we don't have to worry about anymore, because we'll let someone like Amazon or Microsoft Azure handle for us, and bringing about a new way of computing. Many of your mobile applications running on your phone are cloud-based applications. Agent-based computing is when we have systems which are conveniently modeled by many different nodes, and each of those nodes has a small computer on it. Then those computers, or what we'll call agents, can communicate with each other. The idea being somewhat bio-inspired. When we look at, let's say, the ant or the bee, or even the dog, each of these can accomplish a small amount on their own. But when they work together as a swarm of ants, or a hive of bees, or a pack of dogs, they can accomplish much more. We're looking at computing systems that behave the same way. Sensor networks are part of what is becoming the Internet of Things, where everything everywhere will be sensed and reported and hopefully acted upon. Related to this is the idea of SCADA, Supervisory Control and Data Acquisition, where the local system can make some decisions on its own, but we gather that data and ship it back to a monitoring system where we can exert some supervision over that also. The result is that we have cheap, low-power sensors everywhere. We need low-powered networking to connect all these things together. Still quite a bit of work to be done on these. Of course, you're probably familiar with solar and wind power. Over the recent years, these have become more mainstream. You start to see solar power on many buildings, and we see windmills all over the countryside. The picture on the lower left is actually a solar-powered airplane, and there's an organization that is flying a solar-powered airplane both day and night to make a trip around the world, a circumnavigation. All this leads us to a need for superior battery and charging technology. Stanford researchers just announced a battery based upon aluminum that charges very quickly. You can find some recent news reports as of April 2015 about this exciting new breakthrough. This is really electrochemical technology, where we have chemists and electrical engineers working together. Elon Musk, famous for Tesla and a number of other companies, is building a huge factory to make batteries. This will be an important part of our economy going forward. The charging technology is dependent upon the circuit design and also the active device research. By this I mean the transistors that are used in the electronics to actually charge these very efficiently. And some interesting problems associated with near-field charging. In other words, charge via radio waves, so you don't even need to plug anything in. You just drive up and the car, perhaps, or your phone would. So electrical cars are entering the mainstream, and as mentioned, these require battery technology, charging stations, charging circuits, but also very efficient and controllable electric motors. Another interesting thing is that cars are connecting with each other and featuring collision avoidance. Now we have little radars that are mounted on our bumpers to determine, make sure that we're not closing in on a car ahead of us too quickly. And these cars can send each other information about traffic conditions ahead. Along with this new energy paradigm of trying to generate this with solar and wind, we're looking at the smart grid to improve the distribution and the usage of electricity, and to be able to put a much finer amount of control on these usages of electricity, and importantly to ultimately go to demand pricing, so that we can encourage people to use electricity when the demand is low by offering them a low price. Remote sensing is another important area that electrical engineers are very involved with. This is one of my projects. This is the GOES weather satellite, and includes a number of different functions on this satellite. You're most familiar with it if you watch the weather or look at weather maps on your computer, and those maps and images are coming from a family of geosynchronous Earth observing satellites, and they also include a number of other functions, including some emergency locator type of technology for finding people that are in trouble anywhere in the world if they have the right type of transponder, and also gathers telemetry from weather stations all around the world. In contrast to that big, huge satellite, which is probably as big as your electronics lab, we are now looking at using CubeSats, where now the satellite is small enough to fit in the palm of your hand, but correspondingly it can't do a whole lot just on its own. But again, we fly a bunch of these in a swarm, and we can communicate together with them, and now we have one of these agent-based networks. And these satellites are much easier to launch, much cheaper to build and launch, and it's an exciting new field, trying to see if we can change the way satellites are built, launched, and managed. Computer networking is all around us, and as you might expect, we want to be connected at faster and faster rates and in more remote areas. Machines are actually connecting to other machines in a field called M2M, or machine to machine. This is related to the Internet of Things, where we're bringing connectivity to many, many, many more things. But all this implies security, security, security. And that's going to be one of the most important fields of engineering and of computer science going forward. Finally, a current topic of research is software-defined networking, where we're implementing more and more of the network functions in software to be able to adapt our networks on the fly. So, is it hardware or is it software? I've found that more and more hardware is reconfigurable via software or software-like processes. More and more software relies upon alternative hardware configurations. The lines are getting blurry. Computer engineering is a great field to be in, to have great, strong skills in these areas. Let me finish with a brief example of my career. I started in surface acoustic wave resonator filters. This is a piezoelectric device that is used in radio systems. Piezoelectric means that it is built on a crystal that includes both mechanical and electrical effects, and they are coupled together. We can also use these to make chemical sensors, and we can look for environmental pollutants or perhaps even chemical warfare agents. I did those for probably 13 years, I think, and then left that field to go write software commercially. And one of the first projects I did was to manage the FAA airways system. In other words, to monitor the status of all the radars and runway lights and radio systems all throughout the FAA system throughout the country. I then left that to go write online clinical record software, which is one of the earliest systems where doctors actually entered your medical records right into the computer rather than on that paper chart. I want you to understand the diversity of the career that I've had. I went from there to work as a one-man software department alongside a one-man electrical engineering department and alongside a one-man mechanical engineering department in a little tiny company that did GPS-based fleet management systems, and worked in that for about 5 years, at which time I decided that I missed the electrical engineering part of it, and so went back to get my PhD. Along the way, I did a lot of research in what we call cognitive radio, and I'll just give you some buzzwords here. Worked on argumentation-based negotiation and complex distributed decision-making. It's an artificial intelligence multi-agent type system. I've worked on a graphics processor unit, field programmable gate array, superconducting, analog to digital conversion, satellite communication receiver. That's a mouthful. I've recently worked on a 20 kilowatt radio power amplifier for improvised explosive device defeat, and also has applications in particle accelerators. And done a lot of work in digital pre-distortion to linearize power amplifiers for 4G LTE type systems. And have worked with a lot of waveform level theoretical development in LTE Advanced, which you thought your phone was pretty cool with just having LTE, but yes, of course, we're working on LTE Advanced and 5G communications. But now, after a 30-year career in industry, I've started my later career as an educator. So in conclusion, electrical and computer engineering are both very social fields. They are diverse with many challenges. If you would like to work in one particular field your whole career and become a world-class expert, you have that opportunity. If you would prefer more diversity and new challenges in your career, then you can find plenty of different things to work on as your career evolves. One of the things I like about it is that it's involved in many different areas of our lives and is one of the forces powering our economy. Thank you.